Most of the prompt gamma radiation is deposited between 25 and 30 kilometers altitude. The air molecules are ionized, and the free electrons split off and start spiraling around the magnetic field lines. Each spiraling electron emits minute radio waves. All of the electrons exist nearly simultaneously, and the minute radio waves add together. This is the primary source of the high-altitude electromagnetic pulse, or EMP, which is a broadband pulse of radio frequency energy radiated from the deposition region. When this electromagnetic pulse is coupled into a system, very large voltages and currents may be induced. Other EMP generating mechanisms are operative in other burst regimes, but are outside the scope of this film and will not be described. The fireball and debris materials rise to maximum heights of from 100 to 1,000 kilometers as the burst height is raised from 50 kilometers to the 100-kilometer region. Unlike debris from the lower explosions, material from the higher explosions falls back from its maximum altitude, ultimately settling around 200 kilometers. With rising burst altitude, greater quantities of beta particles and charged debris particles will shuttle north and south along the magnetic field lines to conjugate points in both hemispheres. Both beta ray and debris interaction with the atmosphere at those points will, for a number of hours, create significant ionization with vivid auroral effects and radio disturbances. Debris gamma and beta radiation will also enhance ionization in the D region at both conjugate points. Other phenomena associated with irregular structure in nuclear burst ionized regions are also important to communications, infrared, and radar systems. One is the eventual development of magnetic field-aligned filaments, or stria, in ionized regions. This film is concerned with the effects of high-altitude nuclear explosions on radars, optical sensors, and communications. To understand how nuclear explosions affect such systems, it is first necessary to understand the interaction of explosions with the atmosphere. Above about 90 kilometers, radiation increasingly breaks more of the molecular gases into their atomic or single atom state. This dissociation, primarily from the ultraviolet radiation, affects as much as 50% of all molecules at altitudes of about 100 kilometers. The cosmic and particle radiation also causes ionization. Detachment of the single electron leaves the remainder of the atom or the molecule with a positive charge. Because of the strong recombination tendency, ionized gases will not remain in that condition unless there is a constant supply of energy to cause new ionization as fast as the previous ions can recombine. The first significant quantities of naturally occurring free electrons begin to show up at an altitude of approximately 60 kilometers, which we therefore consider as the bottom of the ionosphere. From there on up to heights of several hundred kilometers, free electrons become more and more prevalent. Now, in what way do high-altitude nuclear explosions affect these free electron densities? To begin with, roughly 70% of the total energy produced in a nuclear explosion is emitted in less than a microsecond as a flash of X radiation. A few percent more of the bomb energy is emitted as prompt gamma and neutron radiation. Most of the remaining energy appears as directed motion or kinetic energy of the expanding explosion debris. Delayed gamma and beta radiation from this radioactive debris material emits some 5% of the total weapon energy over a longer period of time. We will examine the effects on the atmosphere of nuclear detonations at 50 kilometers, 100 kilometers, and 250 kilometers altitude. First, let us consider the events that follow the detonation of a sub-megaton weapon at a moderate altitude of 40 to 50 kilometers. Most of the X-ray energy is deposited near the burst point, heating air to incandescence. The prompt gamma and neutron radiations from the explosion can, on the average, travel large distances before colliding with air particles. Therefore, the ionization caused by such collisions is spread out laterally over a region several hundred kilometers in diameter. Coming back to our explosion, the X-rays heat the surrounding air to incandescence. Within a tenth of a second, the tremendous radiant energy output and gas expansion processes have created a fireball of superheated air several kilometers in diameter. Inside the fireball, both the air and the smaller central mass of expanding weapon debris are fully dissociated from the molecular into the atomic state, and the atoms themselves are highly ionized. In another view, a high-velocity shock wave is seen to race outward from the radiation front, which is still at a temperature on the order of 10,000 degrees. The fireball expands at a slower rate to a diameter of 10 kilometers within about 5 seconds, during which time it also begins rising upward at a rate approaching 300 meters per second due to the buoyancy of its heated low-density gases. We watch the remainder of the explosion development through a camera located directly underneath the fireball. Sometime during the first minute, the rising cloud of fireball and debris material from explosions at this or lower altitudes interacts with the surrounding air, and the fireball transforms into a torus or donut shape. Both gammas and high-energy electrons or beta rays are continuously emitted from fission fragments in the debris. The cooling fireball and debris mixture, no longer luminous, continues to rise and expand, reaching a diameter of about 40 kilometers at 1 minute. It finally stabilizes some minutes later at an altitude of about 100 kilometers until dissipated by atmospheric winds. We will next consider a nuclear explosion of large yield at an altitude of 100 kilometers, where the atmosphere is less than 1,000th as dense as it was at 50 kilometers. The initial heavily ionized X-ray fireball will be an order of magnitude larger than from our low-altitude shot and much more tenuous and less brilliant in appearance because so much of the X radiation escapes to large distances, over which it causes a significant ionization increase without luminosity. The atmosphere is so rarefied that the highly penetrating prompt gamma and neutron radiation from the explosion will produce only negligible concentrations of new ions in horizontal and upward directions. Ions are produced in the D layer and at lower altitudes. The hot and rapidly expanding fireball rises ballistically with something over 5 times the average velocity seen for the lower shot. Its diameter is some 300 kilometers after the first minute. Magnetic forces progressively distort the rising material, elongated along the geomagnetic field lines. Maximum altitude on the order of 1,000 kilometers is reached in 7 or 8 minutes. With the upward ballistic impulse exhausted, the material, being heavier than the ambient atmosphere, tends to fall back to denser regions on the order of 150 to 200 kilometers. The fall is oriented primarily along the Earth's geomagnetic field lines. The diameter is several hundred kilometers with a thickness perhaps a tenth as great. Actually, being electrically charged, the beta particles are constrained to follow the Earth's geomagnetic field lines. Thus, a region of ionization commonly called the beta patch is caused by these downward traveling electrons. The few beta particles that start out parallel to the field line will continue to follow them. If the particles encounter the field lines at an angle, however, they will spiral around them. Here we see beta particles streaming along the magnetic field through the fireball and debris of a burst. Those electrons ejected upward may be trapped along the Earth's magnetic field lines and are mirrored back and forth if the reversal or mirror point is substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle and soon will be lost by collision with air molecules. This collision excitation mechanism is generally accepted as one of the causes of auroral displays. Thus, a nuclear burst at sufficiently high altitudes can produce auroras at conjugate points in both hemispheres. Since the debris from a nuclear detonation begins radiating at the moment of the explosion, its conjugate point auroral effects can be expected to change location as the debris rises and intersects with successively higher magnetic field lines. Note that when the debris is located below about 200 kilometers, most of the electrons shuttling along the field lines will be lost in the atmosphere on their first pass, with very little mirroring back to the other conjugate point. We will next consider a nuclear explosion at altitudes above 250 kilometers. Mass asymmetries in the construction of the nuclear device and its carrier can be very important and are observable in this 400-kilometer explosion. At this very high altitude, a substantial change occurs in the mechanism of containment, the forces which slow and finally stop fireball and debris expansion. While ordinary hydrodynamic pressure resists the explosion expansion at low altitudes, geomagnetic back pressure becomes increasingly important at altitudes above 100 kilometers. The heavily ionized debris and gases in an expanding fireball are electrically conductive, so the Earth's magnetic field tends to be excluded from that region, creating a so-called magnetic bubble, which presses back against the expanding gases.
This initial exploration in 1958 was limited to 6 shots. From a ship in the South Atlantic, 3 small detonations, known as the Argus series, were launched and triggered aloft for the purpose of examining the Christophilus theory that a long-lived belt of trapped electrons could be artificially created by a very high-altitude nuclear explosion. Yucca, Orange, and Teak were detonated at respectively 26, 43, 77 kilometers, primarily to provide information on the change of blast, nuclear, and thermal effects with increasing altitude. At an approximate altitude of 85,000 feet, Yucca was detonated by radio command signal. Yucca produced a bright fireball with a center core, which rapidly developed into a toroid similar to the teapot and plumbob altitude shots. The major part of the thermal pulse lasted about 30 milliseconds, with some perceptible signal for as long as 500 milliseconds. A double maximum was observed in the first part of the pulse, followed by a minimum at 2 milliseconds, then a second maximum at about 13 milliseconds. The teak fireball expanded very rapidly for the first 100 microseconds, reaching a diameter of 10 miles in 10 milliseconds. The teak infrared fireball was almost 40 miles in diameter at h plus 1 second, after which it disappeared quickly. The orange fireball expanded more slowly, reaching a diameter of approximately 1.5 miles in 10 milliseconds. The orange infrared fireball, although of the same diameter, lasted somewhat longer than teak. Teak produced a single thermal peak at about 500 microseconds, decaying to less than 25% of the peak value in about 10 milliseconds. The corresponding times for a sea level burst would be 2 seconds to second maximum, and 6 seconds for the pulse to decay to 25% of peak radiance. The rapid expansion of the early fireball was spectacularly different from a sea level shot. The lower orange shot showed a transition situation with the thermal pulse indicating some of the characteristics of a lower altitude shot, intermediate between teak and surface bursts. There were 2 peaks, the first of brief duration reaching a maximum at 500 microseconds, and the second consisting of a broad flat maximum lasting from 100 to 300 milliseconds. The spectra of orange consisted of a strong emission continuum with molecular band absorption superimposed. Damage by thermal energy to the retina or to the choroid will leave permanent scars or lesions which will not result in impairment of vision, nor is pain associated with such burns. However, if the burn occurs on the macula, loss of central vision and visual acuity will result. The phenomenon of chorioretinal burn is distinct from that of flash blindness, which is the temporary loss of vision resulting from lesser amounts of thermal energy than that required to produce burns on the inner eye. For the teak shot, animal stations were located on Johnston Island, on aircraft and ships out to 300 nautical miles. Each station had instrumentation to record the thermal input. On teak, chorioretinal burns were produced on all rabbits exposed, except on the surface ship at 300 miles, where clouds and ship roll may have prevented the rabbits from viewing the initial flash. On orange, cloud cover interfered with the surface stations, but burns were received in the aircraft at 225 miles. Retinal burn diameter consistently correlated with distance from burst zero. The lesions produced at all exposure stations within 160 nautical miles were of sufficient size and severity to result in permanent retinal damage or severe loss in visual acuity. Thus, theory is verified that megaton nuclear explosions at the altitudes tested produced chorioretinal burns at great distances as a result of the rapid rate at which the thermal energy is delivered. Most of the energy is delivered before the effective blink reflex time of 250 to 350 milliseconds for rabbits and 100 to 150 milliseconds for man. Johnston Island had a slant range of 252,000 feet from shot teak. The overpressure measured approximately 0.1 pounds per square inch. The same station at a slant range of 196,000 feet from shot orange measured 0.18 pounds per square inch. At 50,000 feet during teak, the gamma dose rate was about 300 milliröntgens per microsecond at 5 milliseconds. During orange, the gamma dose rates at 5 milliseconds were about 1,000 milliröntgens per microsecond at 30,000 feet slant range and 10 milliröntgens per microsecond at 100,000 feet. The gamma ray measurements were consistent between pods. Less force is transmitted by blast, while thermal and nuclear radiation are both more intense and extensive in area. Most spectacular was the extent of the fireball growth on teak, the highest of the 3 shots, a diameter of 10 miles in 10 milliseconds, accompanied by a striking visual aurora. On Operation Fishbowl, nuclear detonations rent the sky 5 times over the Johnston Island area, each time during the hours of darkness. The highest burst was the 400-kilometer Starfish event, launched by a pod-carrying Thor missile. Its yield was 1.4 megatons. In addition to the local phenomena, the transport of bomb debris and other charged particles in the magnetic field produced colorful aurora, arcing into the northern and southern conjugate regions. Checkmate, like Starfish, did not display a well-defined fireball. Checkmate exhibited a moderate aurora seen in both the northern and southern conjugate areas. Kingfish's fireball was well defined and its aurora moderate.